Look up at the night sky, and you'll see a tapestry of light, each star a distant sun, some burning bright, others already gone. But here's the thing, when a star dies, it doesn't just vanish. It leaves behind a story written in cosmic fireworks, ghostly nebulas, and remnants that echo across the universe. What if I told you these stellar deaths hold clues to some of the biggest mysteries in astronomy? From the explosive fury of supernova to the delicate filaments of supernova remnants, these events aren't just endings, they're gateways to understanding everything from the birth of new stars to the very elements that make up our world. Think about this for a moment. Every atom in your body, the iron in your blood, the calcium in your bones, they were forged in the heart of dying stars. That's right, you're literally made of stardust, and yet, despite knowing this, we're still unraveling the secrets of how these stars meet their fate. Why do some collapse silently into black holes while others tear themselves apart in dazzling supernova? How do the remnants they leave behind shape the galaxies we see today? These questions have driven astronomers to the edge of discovery, using everything from space telescopes to supercomputers to piece together the puzzle. This isn't just a story about stars, it's a story about us, our curiosity, our relentless drive to understand the cosmos, and the way these celestial phenomena connect to the grand narrative of the universe. Over the next few minutes, we'll explore 26 of the most fascinating mysteries and breakthroughs in the study of dying stars and their remnants. You'll witness the violent beauty of supernova, the eerie glow of nebulas, and the cutting-edge science that's rewriting what we know about stellar life cycles. By the time we're done, you won't just see the night sky differently, you'll feel it. So let's begin this journey, because the universe has secrets to share, and they're more incredible than you've ever imagined. Imagine a star massive, luminous, burning brighter than a million suns, simply vanishing from the night sky. No explosion, no grand finale, just gone. This isn't science fiction. It's one of the most perplexing enigmas in modern astronomy, the case of the phantom supernova. Normally, when a massive star reaches the end of its life, it goes out with a bang, a supernova so powerful it can outshine entire galaxies. But some stars defy expectations, disappearing without a trace, as if swallowed by the cosmos itself. What's really happening here? One leading theory suggests these stars might collapse directly into black holes, skipping the explosive stage entirely. Think of it like a building imploding inward instead of exploding outward, a silent, invisible collapse. Advanced computer simulations support this idea, showing how certain stars could simply crumple under their own gravity, vanishing into darkness. But catching this process in action is like trying to photograph a shadow in a pitch-black room. The evidence is fleeting, and the clues are maddeningly subtle. This mystery isn't just about missing stars, it's a challenge to our entire understanding of stellar evolution. For decades, astronomers relied on supernova as cosmic mile markers, using their brilliant flashes to measure distances across the universe. But if stars can vanish without warning, what does that mean for our models? Could there be an entire population of failed supernova hiding in the data, quietly skewing our cosmic calculations? And here's the real kicker. If these silent collapses are happening, they might explain another puzzle: the surprising number of black holes we've detected in recent years. If massive stars are slipping away unnoticed, they could be seeding the universe with far more black holes than we ever anticipated. It's a cosmic game of hide and seek, and astronomers are just beginning to learn the rules. So the next time you gaze up at the night sky, remember, not all stellar deaths are created equal. Some stars go out in flames, while others fade into the void, leaving behind only questions. And as we peel back the layers of this mystery, we're not just solving a puzzle, we're rewriting the story of how stars live, die, and shape the universe around us. When we picture a star exploding, we often imagine a perfect sphere of fire, a brilliant, symmetrical burst of light and energy. But nature rarely follows our neat expectations. The truth is far more chaotic. Supernovae are cosmic rebels, tearing themselves apart in lopsided, unpredictable ways. Take Cas A, one of the most studied supernova remnants. Instead of a smooth shell, it's a tangled wreckage of twisted filaments, jagged arcs, and rogue jets shooting debris at breakneck speeds. This isn't a fluke, it's the norm. So why do stars, which spend their lives as near-perfect spheres, die in such spectacularly messy fashion? The answer might lie in what's happening deep inside a star in its final moments. As the core collapses, it doesn't just give up evenly. Turbulence, magnetic fields, and rapid rotation can create violent imbalances, like a spinning top wobbling out of control. Picture a pot of boiling water. Bubbles don't rise in neat lines, they churn and spiral unpredictably. Now scale that up to a star with the energy of 1 billion suns, and you start to understand why supernovae don't play by symmetrical rules. Some researchers even suspect hidden companions nearby stars or black holes might tug on the dying star's outer layers, warping the explosion like a gravitational fingerprint. But here's where it gets even more fascinating. This asymmetry isn't just a cosmic curiosity, it's a delivery system for life itself. Those lopsided explosions fling heavy elements, carbon, oxygen, iron, into space at different speeds and directions. Without this chaos, these building blocks might not spread far enough to enrich future stars, planets, or even us. Think of it like scattering seeds in a garden. A perfectly round explosion would drop them all in one spot, but a messy, asymmetrical blast ensures they reach every corner of the cosmic soil. This revelation is forcing astronomers to rethink decades of models. If supernovae aren't spherical, their energy, their light, even their role in galactic evolution might work differently than we assumed. It's like discovering that every fireworks show you've ever seen was actually half hidden until now. And with cutting-edge tools like the James Webb Space Telescope peering into the heart of these explosions, we're finally starting to map the true shape of stellar death. One thing's certain, the universe prefers its drama with a twist, and as we untangle these asymmetrical secrets, we're not just solving a puzzle, we're learning how chaos writes the story of life itself. Every time you take a breath, you're inhaling atoms created in the heart of a dying star. That gold ring on your finger, forged in a supernova's unimaginable heat. The calcium in your bones, a stellar relic billions of years in the making. This is cosmic alchemy at its finest, the breathtaking process where ordinary stars transform into elemental factories during their final, fiery moments. But here's what's truly astonishing. We're only now beginning to decode exactly how these celestial forges operate. Take iron, for instance, the very element that makes your blood red. In a star's final hours, temperatures soar beyond 100 billion degrees, hot enough to smash atoms together with such force that lighter elements fuse into heavier ones. This isn't just simple fusion. It's an atomic ballet where protons and neutrons rearrange themselves under extreme pressure, forming entirely new substances. But spectroscopy, the science of reading light from distant stars, has revealed something peculiar. Some elements, like gold and platinum, appear in far greater quantities than our models predicted. It's as if nature has a secret recipe we haven't quite uncovered. One breakthrough came when astronomers studied a supernova remnant called Cassiopeia A. Hidden in its swirling gases were telltale signatures of titanium and chromium elements that shouldn't exist in such abundance unless something extraordinary was happening during the explosion. The leading theory, a phenomenon called the alpha-rich freeze-out, where the supernova's shockwave creates a brief but insanely dense environment, allowing atoms to capture extra neutrons at breakneck speed. Picture a high-speed assembly line where atomic parts snap together in microseconds, creating exotic elements that would never form under normal stellar conditions. But the real magic happens after the explosion. As the supernova's shockwave expands, it catapults these newly forged elements into interstellar space at millions of miles per hour. Over millennia, they mix with giant clouds of gas and dust, eventually becoming part of new stars, planets, and yes, living organisms. That means the carbon in your DNA, the oxygen you breathe, even the zinc that fuels your immune system, all began their journey in a cataclysmic stellar death. What's truly humbling is realizing we're not just observers of this process, we're products of it. Every piece of jewelry, every steel skyscraper, every molecule in your body contains atoms that survived the unimaginable violence of a supernova. And as our telescopes grow more advanced, we're getting closer to reading these stellar fingerprints in unprecedented detail. Who knows what other elemental secrets are still waiting to be discovered in the ashes of dead stars? One thing's for certain, the universe didn't just create us, it cooked us up in the most spectacular kitchen imaginable. Some of the most breathtaking sights in the cosmos come from the graves of dead stars' supernova remnants that glow with an eerie, otherworldly light. Take the Crab Nebula, for instance. Its ghostly tendrils shine so brightly they've been visible from Earth for nearly 1,000 years. But here's the catch. When astronomers crunch the numbers, these luminous remnants shouldn't be this radiant. The math says their glow should fade long before it does, like a light bulb that refuses to burn out. So what's powering these cosmic lanterns beyond their expected expiration date? The answer might lie in forces we're still struggling to understand. Hidden deep within these nebulas, particles whip through space at nearly the speed of light, caught in a web of magnetic fields strong enough to bend atoms. It's like nature's own particle accelerator, far more powerful than anything we've built on Earth. And just like in our labs, when these particles collide, they release energy in dazzling bursts of light. But the scale is mind-boggling. The Crab Nebula's magnetic fields are so intense, they could strip the data from a credit card at a distance of 100,000 miles. Then there's the puzzle of the Veil Nebula. Its delicate, thread-like filaments glow with colors that shouldn't exist based on the elements we know are present. Some scientists suspect an invisible hand might be at work, perhaps the ghostly influence of a pulsar we haven't detected yet, spinning silently at the nebula's heart. Others wonder if something even more exotic is happening, like interactions with dark matter. Imagine a cosmic game of billiards where some of the balls are invisible, yet their effects ripple through the visible world. What makes these remnants so fascinating isn't just their defiance of expectations, it's what they teach us about the universe's hidden rulebook. The same particle acceleration happening inside them might explain how cosmic rays, those mysterious high-energy particles bombarding Earth, get their incredible speed. And by studying these radiant wrecks, we're essentially peering into a natural laboratory where physics operates at extremes we can't recreate. Yet for all their brilliance, some remnants flirt with invisibility. Fainter echoes of supernova blend into the cosmic background, their stories whispered in wavelengths our eyes can't see. These ghosts challenge our telescopes and our theories, reminding us that even in death, stars guard their secrets closely. And as we push our instruments to new limits, We're not just solving a mystery, we're learning how to read the universe's faintest handwriting. If our galaxy were a graveyard for stars, it should be littered with the glowing tombstones of supernova remnants, thousands of them, stretching across the Milky Way's spiral arms. But here's the cosmic detective story no one saw coming. When astronomers tally up the visible remnants, the numbers don't add up. We've catalogued fewer than 300, when theory predicts there should be at least 10 times as many. So where are all the missing shells? Are they hiding in plain sight? Or have we fundamentally misunderstood how stars die? One clue comes from the remnants we can see. Take the faint, wispy structures like G106.3 plus 2.7, a mouthful of a name for a ghostly bubble nearly 100 light-years wide. Discovered only through radio telescopes, it's so delicate that optical telescopes barely register its presence. This raises a tantalizing possibility. What if most supernova remnants aren't missing at all, but have simply expanded so far that they've become nearly transparent? Like smoke rings dissolving in the wind, their gases might thin out over millennia, blending into the interstellar medium until only the faintest radio whispers remain. But there's another twist. Some dying stars might be playing a cosmic vanishing act by exploding in environments we rarely consider. Imagine a supernova detonating deep inside a dense molecular cloud. The surrounding gas could absorb the blast's energy, muffling the explosion like a firework wrapped in a blanket. Without the usual shockwave lighting up the neighborhood, these events could slip past our telescopes entirely. It's like searching for a flashlight in a foggy forest. You might miss it entirely if the conditions are just right. Now enter the game changers, artificial intelligence and next-generation surveys. Projects like the Australian Square Kilometre Array Pathfinder are combing the skies with algorithms trained to spot the subtlest radio fingerprints of these faded remnants. And the results are startling. Recent AI-assisted scans have uncovered bizarre, bubble-like structures that don't match any known supernova models. Could these be the ghosts we've been seeking? Stellar corpses that died in ways we haven't yet imagined. The implications ripple far beyond a simple accounting error. If remnants vanish faster than predicted, it could mean the interstellar medium is far more turbulent than we thought, shredding these structures before they can fully form. Or perhaps some stars collapse so efficiently into black holes that they leave barely a trace. Every missing remnant is a silent witness to a stellar death we failed to record, a gap in our cosmic history books. Yet for every mystery solved, another takes its place. As we peel back the layers of this enigma, we're not just hunting for celestial debris, we're rewriting the rules of how stars live, die, and disappear. And with each new discovery, the universe reminds us, what we don't see might be just as important as what we do. Imagine a star cheating death enduring a supernova's apocalyptic fury only to stagger away, wounded but still burning. These cosmic survivors, nicknamed zombie stars, defy everything we thought we knew about stellar endings. Take LP 4365, a rogue white dwarf racing through our galaxy at nearly 2 million miles per hour. Spectroscopic analysis reveals something impossible. This star shouldn't exist. Its outer layers are littered with neon, oxygen, and magnesium, elements normally buried deep in a star's core. It's like finding a tree with its roots growing out of its branches. So how does a star walk away from its own funeral? The leading theory involves a thermonuclear explosion that's powerful enough to blast away a star's outer layers, but not quite strong enough to finish the job. Picture a firework that misfires, ejecting half its payload while the rest smolders on. For the star, this partial detonation becomes a twisted rebirth. The blast strips away enough material to relieve internal pressure, preventing total collapse, while the remaining core, now exposed and searing hot, reignites nuclear fusion in a last-ditch effort to survive. But the real shocker, some of these stellar phoenixes emerge even heavier than before. Normally, white dwarfs obey the Chandrasekhar limit, a cosmic speed bump preventing them from exceeding 1.4 times the Sun's mass. Yet zombie stars like SDSS J124+040 defy this rule, tipping the scales at nearly twice that weight. Their secret: the supernova's shockwave might compress the surviving core so violently that it creates exotic quantum states, allowing the star to bear more weight without collapsing. It's the cosmic equivalent of a bridge reinforced with materials we've never seen before. What makes these survivors truly fascinating are the scars they carry. Their surfaces often show bizarre chemical cocktails, traces of the explosion frozen in time like ash after a wildfire. By studying these elemental fingerprints, astronomers can reconstruct the exact moment the star's life hung in the balance. Some even sport hydrogen bandages, stolen gas from neighboring stars that reignited fusion like jumper cables on a dead battery. Yet for all we've learned, zombie stars raise more questions than answers. Why do some stars fail to explode completely? Could our own sun's death play out differently than we predict? Every new discovery blurs the line between stellar life and death, proving that in the cosmos, endings are rarely as final as they seem. And as we uncover more of these celestial undead, we're not just rewriting astronomy textbooks, we're learning that stars, much like the best stories, sometimes refuse to end when they're supposed to. For decades, astronomers have treated supernova like cosmic fireworks, predictable explosions triggered by a star's inevitable collapse. But the more we study these stellar detonations, the clearer it becomes we're missing the spark. Picture standing before a towering pile of dry timber, matches in hand, yet no matter how many times you strike, the fire won't catch. That's essentially where supernova research stands today. Our simulations can recreate 99.9% of a star's death throes, but that critical moment when collapse becomes explosion, that final 0.1% remains one of the greatest unsolved puzzles in astrophysics. The heart of the mystery lies in what scientists call the bounce. As a massive star runs out of nuclear fuel, its core, now mostly iron, can no longer resist gravity's crushing grip. In milliseconds, it shrinks from the size of Earth to a sphere just 12 miles across, reaching densities beyond comprehension. At this point, conventional wisdom says the collapse should rebound, sending a shockwave tearing through the star's outer layers. But here's the catch: in every computer model, that shockwave stalls. Like a car engine turning over but never starting, the simulation freezes with the explosion stillborn. Something must be giving it that final push, but what? Neutrinos, those ghostly particles that barely interact with matter, might hold part of the answer. During the core collapse, so many neutrinos flood outward that they carry away 99% of the star's energy, enough to power the explosion theoretically. Recent detectors like Japan's Super Kamiokande have caught neutrinos from distant supernova showing peculiar energy patterns, suggesting they might transfer just enough oomph to reignite the stalled shockwave. It's like discovering that the quietest person in the room has been whispering secret instructions all along. Yet even with neutrinos in the equation, the numbers still don't quite add up. Then there's the wild card, quantum turbulence. At the insane densities of a collapsing core, protons and neutrons stop behaving like discrete particles and instead form a bizarre quantum soup. Some theorists believe microscopic whirlpools in this soup could create pockets of extra pressure, giving the shockwave random boosts like hidden trampolines scattered through the star's interior. Others point to pre-collapse instabilities, where slight asymmetries in the star's rotation or magnetic fields amplified during collapse twisting the explosion like a corkscrew. The Kepler supernova remnant, with its bizarre three-lobed structure, might be the smoking gun for this theory. Perhaps most intriguing are the tipping point stars, those hovering right at the edge of stability. For these stellar tightrope walkers, something as subtle as gravitational waves from a nearby black hole merger or an influx of dark matter particles might provide the nudge needed to trigger collapse. It's the cosmic equivalent of a snowflake causing an avalanche, where tiny, almost imperceptible forces can unleash unimaginable violence. What makes this mystery so urgent isn't just academic curiosity. Supernova are the universe's primary element factories, and even slight variations in how they ignite could explain why we find unexpected abundances of gold, uranium, and other heavy elements across the cosmos. Moreover, since astronomers use these explosions as standard candles to measure cosmic distances, misunderstanding their trigger mechanism might mean we've been misreading the scale of the universe itself. As new telescopes come online capable of catching stars in their final hours and neutrino detectors grow more sensitive, we're inching closer to solving this celestial murder mystery. One thing's certain: when we finally witness that critical moment of ignition, it won't just answer a question, it will rewrite the story of how stars die, how elements spread, and perhaps even how life itself became possible. The universe has been keeping its detonation codes locked away, but not for much longer. Picture this: a star shining steadily for millions of years suddenly starts flickering like a candle in the wind. Its light dims unpredictably, throwing off strange bursts of energy, not quite an explosion, but not normal either. Then, months later, it detonates in a supernova visible across the galaxy. Were those earlier tantrums a cry for help, a cosmic distress signal warning of its impending demise? This is the tantalizing mystery of Precursor signals, the subtle hint stars might give before they self-destruct. And if we can learn to read them, we might unlock the ability to predict stellar deaths like never before. One of the most compelling cases came from Supernova 2023 IXF, a massive star that erupted in a nearby galaxy. Months before its final explosion, telescopes caught it undergoing bizarre convulsions, violent hiccups of brightness followed by eerie quiet. Astronomers scrambled to analyze the data, and what they found was astonishing. The star wasn't just dimming randomly, it was ejecting massive shells of gas in fits and starts, like a patient coughing before a fever breaks, the leading theory. Deep inside the star, the core was already destabilizing, sending shockwaves through its outer layers long before the final collapse. It's as if the star's heart was faltering, and its surface was the last to know. Then there's the neutrino factor. These elusive particles, so tiny they pass through planets like ghosts, might be the universe's ultimate early warning system. In 1987, detectors on Earth caught a burst of neutrinos arriving 3 hours before light from supernova 1987A. Why? Because neutrinos escape the collapsing core almost instantly, while light gets trapped in the chaos. Today, projects like the Supernova Early Warning System monitor neutrino observatories around the clock, ready to alert telescopes the moment these particles whisper of a star's impending doom. Imagine getting a cosmic text message: "Supernova in progress, look now." But not all precursor signals are so straightforward. Some stars, like the infamous Betelgeuse, tease us with dramatic dimming only to bounce back like nothing happened. In late 2019, this red supergiant dimmed by 60%, sparking rumors of an imminent explosion. But instead of going supernova, it coughed out a cloud of dust and carried on. Was this a false alarm or a rehearsal for the real event? The answer might lie in the star's inner turmoil. Massive stars like Betelgeuse experience violent convection currents. Think of a boiling pot the size of Jupiter that can slosh material to the surface unpredictably. Separating these normal tantrums from true death throes is like distinguishing a sneeze from a heart attack. The stakes couldn't be higher. If we can reliably predict a supernova, even by minutes, it would revolutionize astronomy. Telescopes could capture the explosion's first light, tracing how the shockwave tears through the star's outer layers in real time. We might finally see the moment a neutron star or black hole is born. And beyond the science, there's something profoundly human about the idea, a chance to bear witness to a star's final act, to say, "We saw you coming, and we were watching when it happened." Yet for every clue we decipher, the universe throws us a curveball. Some supernova erupt without warning, silent until the moment they rip themselves apart. Others flicker for decades before their grand finale. It's a reminder that stars, like living things, don't follow scripts. They die as they lived, unpredictably, violently, and on their own terms. And as we piece together their final whispers, we're not just solving a puzzle, we're learning to listen to the cosmos in a whole new way. When a supernova's fury fades, most remnants settle into one of two familiar forms, either a neutron star, that ultra-dense cosmic cinder, or a black hole, nature's ultimate vacuum cleaner. But sometimes the universe tosses us a curveball, remnants so bizarre they defy textbook explanations. Take Magnetars, for instance. These neutron stars on steroids boast magnetic fields a quadrillion times stronger than Earth's, so powerful they could erase every hard drive on our planet from halfway across the galaxy. Yet their origins remain shrouded in mystery. Why do some collapsing stars birth these magnetic monsters while others don't? The leading theory suggests it's all about spin. During a supernova, if the dying star's core rotates fast enough, think hundreds of times per second, its tangled magnetic fields might get amplified to ludicrous levels, like a dynamo cranked to apocalyptic settings. We've spotted fewer than 30 confirmed magnetars, but their outbursts are unforgettable. In 2004, one named SGR 1806 20 blasted gamma rays so intense they ionized Earth's upper atmosphere from 50,000 light-years away. It's the cosmic equivalent of a flashlight momentarily outshining the sun. Then there's the real wildcards, quark stars. These hypothetical remnants might form when neutron stars get squeezed beyond their limits, crushing protons and neutrons until they dissolve into a soup of free floating quarks. Picture a diamond compressed until its atomic structure shatters, leaving behind something entirely new. While no quark star has been definitively confirmed, candidates like XTJ 1739-285 tantalize researchers. Its temperature and radiation patterns don't quite match a neutron star's profile, as if it's hiding an exotic core beneath its surface. But the strangest relics might be the ones we can't see at all, black widow pulsars. These neutron stars orbit so close to companions that their radiation slowly evaporates the other star, leaving behind a ghostly residue. PSRB 1957+20, for example, has reduced its partner to a planet-sized cinder, just 2% the Sun's mass. It's stellar vampirism on a cosmic scale, where the predator outlives its prey by billions of years. What makes these exotic remnants so revolutionary isn't just their oddity, it's the extreme physics laboratory they represent. Magnetars could help explain fast radio bursts, those enigmatic cosmic sirens. Quark stars might reveal how matter behaves at densities so high even atoms lose meaning. And lurking in the shadows could be even weirder possibilities, strange stars made of up, down, and strange quarks or prion stars composed of hypothetical subquark particles. The deeper we look, the clearer it becomes. The afterlife of stars is far richer than we imagined. These outliers aren't just cosmic oddities, they're keys to unlocking regimes of physics we can't recreate on Earth. And as our telescopes grow sharper, we might find that what we call exotic today is far more common than we ever dared to dream. Most supernovae die in the stellar equivalent of a crowded city, exploding amidst the bustling neighborhoods of their host galaxies. But every so often, astronomers spot a cosmic maverick, a supernova detonating in the vast, empty darkness between galaxies, where no star should logically exist. These intergalactic supernovae are like solitary fireworks erupting over an endless ocean, their light traveling across millions of light-years of pristine void before reaching our telescopes. The question isn't just how they got there, it's what their isolation reveals about the hidden highways of the universe. One leading theory involves rogue stars, violent outcasts flung from their home galaxies during cosmic collisions or gravitational tugs of war. Picture a stellar pinball game where close encounters with supermassive black holes or dense star clusters can accelerate stars to escape velocity, sending them careening into intergalactic space. These nomads might wander for billions of years before finally exhausting their fuel and collapsing in splendid isolation. Supernova 2014J, discovered in the Virgo cluster's emptiness, fits this profile. Its spectral fingerprints matched a white dwarf explosion, suggesting it was once part of a binary system torn apart by galactic tides. But not all intergalactic explosions play by these rules. Some, like the inexplicably bright SN 2011 Phi, defy classification. Located over 300,000 light-years from its nearest galaxy, this supernova burned twice as long and shone far brighter than typical white dwarf detonations. Intriguingly, its light curve hinted at a shell of pre-existing material around the star, as if it had been coughing up gas long before its final demise. This raises a tantalizing possibility. Could dark matter be involved? Hypothetical dark matter particles annihilating in a star's core might provide extra heat, altering how it dies. While speculative, the idea isn't pure fantasy. Dense dark matter halos between galaxies could theoretically shepherd wandering stars, influencing their life cycles in ways we're only beginning to explore. What makes these loners scientifically priceless is their journey through the cosmic wilderness. Unlike galactic supernova, whose light must navigate dust clouds and magnetic fields, intergalactic explosions shine through the cleanest stretches of the universe. Their light arrives undistorted, offering astronomers a crystal-clear measuring stick for cosmic distances. When researchers compared the observed brightness of SN 2014J with theoretical models, they found a discrepancy that hinted at gaps in our understanding of universal expansion. It's like discovering a stopwatch that ticks slightly differently in deep space, a clue that the fabric of reality might stretch unevenly across the cosmos. Yet for every answer these solitary explosions provide, they birth new riddles. Some intergalactic supernova appear younger than the time it would take for a star to drift so far from its birthplace. Others show chemical compositions unlike anything seen in galaxies. Are we witnessing the deaths of stars born in the void itself, condensing from rogue gas clouds too sparse to form full galaxies? Or could some be the remnants of ancient, disintegrated dwarf galaxies, their final stars flickering out like dying embers? The more we study these outliers, the clearer it becomes. The universe doesn't just build stars in predictable factories. It scatters them across the darkness, lets them live and die in ways that challenge our textbooks. And as telescopes like the Vera Rubin Observatory come online, capable of scanning the entire visible sky every few nights, we're bound to find more of these cosmic hermits. Each one is a message in a bottle, cast adrift from the edge of known physics, waiting to tell us how much we've yet to learn. Imagine a supernova so bright it eclipses an entire galaxy, not for days but for months. These are superluminous supernova, cosmic detonations that defy every textbook on stellar deaths. First spotted in 2005, these monsters pump out more energy in weeks than our Sun will emit across its entire 10 billion-year lifespan. What could possibly fuel such apocalyptic fireworks? The answer might rewrite our understanding of how stars die. One leading suspect is a newborn magnetar, a neutron star spinning nearly 1,000 times per second. As its unimaginably strong magnetic field breaks the rotation, it could convert that kinetic energy into light, like a cosmic dynamo on overdrive. Supernova 2007Bi, one of the brightest ever recorded, fits this profile perfectly. Its light curve didn't just fade smoothly, it plateaued for months, as if something inside kept pumping energy into the expanding debris. But here's the catch. Even magnetar models struggle to explain the sheer luminosity of events like Assassin 15LH, which briefly outshone the Milky Way by a factor of 20. Then there's the pair instability bomb scenario. In stars weighing between 140 and 260 solar masses, core temperatures get so extreme that gamma rays start spawning electron-positron pairs. This steals energy from the star's supporting pressure, causing catastrophic collapse followed by runaway thermonuclear detonation. The result, a star doesn't just explode, it annihilates itself down to the last atom, leaving no black hole or neutron star behind. The chemical fingerprints of superluminous supernova remnants support this theory, with layers of silicon, oxygen, and titanium flung outward in precise ratios predicted by pair instability models. But the real puzzle isn't just their brilliance, it's their fleeting aftermath. While normal supernova remnants glow for millennia, these titanic explosions fade within years. The Crab Nebula, a typical supernova remnant, still radiates powerfully 960 years post-explosion. In contrast, superluminous remnants like the one from PS110Z-Y appear to dissipate their energy into space almost apologetically, as if embarrassed by their own violence. Some theorists suggest this rapid fading hints at an invisible accomplice, perhaps a pre-existing shell of gas ejected by the dying star, which the supernova shockwave heats to incredible temperatures before blowing it entirely into the cosmic void. What makes these events truly groundbreaking is their potential link to gamma ray bursts, the universe's most powerful explosions. When astronomers traced the afterglow of GRB 2011 KL, they found it shared eerie similarities with superluminous supernova, from light curve shapes to spectral features. Could some superluminous explosions be gamma ray bursts viewed head-on, their relativistic jets pointing straight at Earth? Or are we seeing an entirely new death mechanism for ultra-massive stars? As for their role in shaping the cosmos, superluminous supernova might be the universe's ultimate sculptors. Their shockwaves can travel hundreds of light-years, compressing interstellar gas into new star-forming regions while simultaneously sterilizing nearby systems with lethal radiation. The iron alone ejected by one such event could seed thousands of future planets, and because they occur preferentially in small, metal-poor galaxies, the kind that dominated the early universe, they might have played an outsized role in cosmic evolution, ionizing vast swaths of primordial hydrogen and lighting up the cosmic dark ages. Yet for all their grandeur, these explosions remain maddeningly rare. Of the million supernova observed since 2005, fewer than 100 qualify as superluminous. Each one is a Rosetta Stone for stellar physics, written in a language we're still learning to decipher. And with next-generation telescopes like the Vera Rubin Observatory poised to catch these ephemeral giants in their infancy, we might soon witness the moment when a star doesn't just die, it rewrites the rules of its own destruction. Supernova aren't just spectacular endings, they're cosmic architects, shaping galaxies with every explosion. Think of them as celestial sculptors, carving voids in interstellar gas while simultaneously compressing nearby clouds into stellar nurseries. This delicate dance between destruction and creation is one of the universe's most intricate feedback loops. When a supernova's shockwave rips through space at millions of miles per hour, it doesn't just scatter elements, it superheats surrounding gas to temperatures so extreme that it glows for millennia. The energy injected into these regions can prevent new stars from forming, effectively putting a galactic neighborhood on pause. Yet paradoxically, the same shockwaves can trigger collapse in nearby gas pockets, jump-starting the birth of stars where none existed before. Take the Orion Nebula, for example. Nestled within its glowing tendrils are dozens of young stars, many likely born from the shockwaves of ancient supernovae. But here's where the mystery deepens. Advanced simulations predict that supernova remnants should keep galaxies in a state of equilibrium, balancing star formation with destructive feedback. Yet when astronomers compare models to real galaxies, the numbers rarely match. Some galaxies, like Messier 82, are stellar factories churning out new stars at breakneck speed, while others, like the Sombrero Galaxy, seem to have shut down production entirely. What's tipping the scales? One clue comes from the remnants themselves. The Crab Nebula's rapidly spinning pulsar injects energy into its surroundings like a cosmic defibrillator, while quieter remnants like G 1.9 plus 0.3 fade into obscurity with barely a ripple. The difference might come down to environment. In dense galactic cores, multiple supernovae can overlap, creating a cumulative wind strong enough to blow gas clean out of a galaxy. But in sparse outskirts, remnants act more like gentle recyclers, enriching local gas without disrupting it. This could explain why galaxies evolve so differently, some growing fat with stars, others starving in a self-imposed drought. Then there's the wild card, dark matter. Invisible halos surrounding galaxies might act like cosmic sponges, absorbing supernova energy and redistributing it in ways we can't yet measure. Simulations that include dark matter interactions show remnants influencing gas dynamics over far greater distances than expected. It's as if the universe has a hidden hand guiding where and when stars are born, with supernova as its paintbrush. The implications stretch beyond our own galaxy. In the early universe, where stars were more massive and supernova far more violent, these feedback loops could have determined whether galaxies grew into spirals like the Milky Way or remained stunted dwarfs. Even now, remnants like Cassiopeia are threading heavy elements into the galactic web, seeding future stars with the ingredients for planets and perhaps life. Yet for all their power, supernova don't act alone. They're part of a symphony of forces, black holes, magnetic fields, even passing galaxies, all tugging on the cosmic tapestry. What makes remnants so fascinating isn't just their individual impact, but how they weave into the larger story of galactic evolution. And as we piece together their role, we're not just solving a puzzle, we're learning how the universe writes its own history, one explosion at a time. Deep within the oldest stars in our galaxy, there are chemical echoes of explosions that rocked the cosmos before Earth even formed. These stellar elders, some nearly as ancient as the universe itself, act like cosmic time capsules, preserving elements forged in supernova that vanished billions of years ago. Take HD 140283, a star so old it's often called the Methuselah star. When astronomers analyzed its atmosphere, they found something astonishing: an unusual abundance of heavy elements like strontium and europium, materials that shouldn't exist in a star this ancient unless it had absorbed debris from a nearby supernova long ago. It's as if we've stumbled upon a cave painting, but instead of pigments, it's written in atoms. What makes these fossil remnants so valuable isn't just their age, it's their purity. In the early universe, before generations of stars had polluted interstellar space with heavier elements, each supernova's chemical signature would have been distinct, like a fingerprint. By studying the ratios of rare earth metals in stars like He 1523-0901, researchers can reverse engineer the properties of the explosions that enriched them. Was it a relatively small star exploding as a Type Ia supernova, scattering iron and silicon, or a colossal hypergiant detonating as a pair instability supernova, dumping titanium and nickel into the cosmos? The answers are literally written in starlight. One of the most revealing cases comes from a group of ultra-metal-poor stars near the galactic halo. These cosmic relics contain barely 1/10,000th the iron of our Sun, making them pristine witnesses to the universe's first stellar deaths. Their composition suggests the earliest supernova behaved differently than modern ones, perhaps exploding with less symmetry or enriching space more efficiently. Some even show traces of radioactive elements like plutonium-244, which decays completely after 100 million years. Finding these isotopes in 12-billion-year-old stars is like discovering unspoiled fruit in a tomb sealed since the Bronze Age, proof that the explosion must have occurred shockingly close to the star's birth. But the real surprise came when astronomers found stars preserving not one, but multiple supernova signatures. The star J0023 plus 0307, for example, shows layers of elements that couldn't have come from the same explosion, evidence that it drifted through several supernova remnants over its lifetime, collecting elements like a ship gathering barnacles. This changes how we view the early galaxy. Instead of stars forming in isolation, they may have grown up in dense, violent clusters where supernova erupted like fireworks on New Year's Eve. Yet these fossil stars also present a paradox. Some contain elements that, according to current models, shouldn't have existed when they formed. Take the star SMSS J2003-22.54-145259.3. Its bizarrely high zinc levels suggest it absorbed material from a supernova triggered by a star with virtually no hydrogen, a type of explosion thought to be impossible in the early universe. Could there have been exotic stellar populations in the cosmos' first chapters, stars that lived and died by rules we haven't yet discovered? As we decode these celestial archives, we're not just piecing together the lives of long-dead stars, we're reconstructing the conditions of the primordial universe itself. Each ancient star is a Rosetta Stone, translating the violent poetry of the cosmos' youth into a language we can finally begin to understand. And with next-generation telescopes like the extremely large telescope set to probe even older stars, we may soon uncover supernova fossils that rewrite the timeline of stellar evolution entirely. The universe has been keeping its diary in stardust for billions of years. Now we're learning how to read it. Stars aren't supposed to die young. Like ancient oaks, they're meant to burn for billions of years before fading unless something catastrophic intervenes. Yet scattered across the cosmos are supernovae that defy this rule, detonating from stars that, by all rights, should have lifetimes longer than the universe itself. Take supernova 2005e, which erupted in the Pinwheel Galaxy. The progenitor star, when traced in pre-explosion images, was a mere 30 million years old, a cosmic toddler compared to stars like our 4.5 billion-year-old Sun. How does a star barely out of its stellar crib end its life in one of the universe's most violent acts? one possibility is that these stars aren't acting alone. Imagine a rogue planet, a Jupiter-sized world flung from its solar system plunging into a young star's core. The sudden infusion of mass could destabilize the star's delicate nuclear balance, triggering runaway fusion like a match tossed into a powder keg. Alternatively, there's the dark matter wildcard. In regions where dark matter clusters densely, these invisible particles might accumulate in a star's core over time. If they occasionally annihilate each other, the resulting energy bursts could heat the core unpredictably, pushing a stable star toward premature collapse. But the most tantalizing explanation involves stellar vampirism. Young stars often form in dense clusters, where gravitational dances can lead to cosmic collisions or binary mergers. If two stars spiral too close, one might strip material from its companion until the victim becomes unstable. Think of a candle wick dipped in gasoline, burning too bright and fast. Supernova 2008 Ha, spotted in a star-forming region of the galaxy NGC 626, showed chemical signatures hinting at this very scenario. Its outer layers were rich in hydrogen stolen from a neighboring star, while its core bore the scars of a violent merger. What makes these premature explosions so revolutionary isn't just their existence, it's what they reveal about stellar resilience. Standard models assume stars live solitary, predictable lives, but the universe clearly has other ideas. Turbulent stellar nurseries, invisible dark matter interactions, or even the gravitational echoes of passing black holes might nudge stars toward early demises we're only beginning to catalogue. Now let's turn to the darkest outcome of stellar death. When a massive star collapses, it doesn't always leave behind a glittering nebula or a spinning pulsar. Sometimes it births a void. Black holes formed from supernova aren't like their supermassive cousins at galactic centers. These are raw, fresh wounds in space-time, often just a few dozen miles wide but containing the mass of several suns. The process of their creation is a ballet of extremes. For a few milliseconds, the dying star's core becomes the densest place in the universe, squeezing matter beyond the breaking point of physics as we know it. Yet even here, mysteries abound. Why do some collapsing stars form black holes instantly, while others linger as neutron stars before crossing the threshold? Recent observations of Supernova 2022 JKX suggest some black holes might form with a failed explosion, the star's outer layers collapsing inward like a deflating balloon, leaving no visible supernova at all. It's cosmic sleight of hand where the universe swallows its secrets whole. What we're learning is that stellar death isn't a single story, it's a library of possibilities, each volume written in the language of gravity, nuclear physics, and pure cosmic chaos. Whether it's a star dying before its time or vanishing into a black hole's shadow, these events aren't just endings. They're invitations to rethink everything we know about how stars live and how they defy our expectations when they die. When a star collapses into a black hole, it doesn't just disappear, it might scream. Not with sound, of course, but with bursts of neutrinos and ripples in spacetime that could carry the unmistakable signature of a singularity being born. For decades, astrophysicists have theorized about this black hole birth cry, a fleeting signal hidden in the chaos of a supernova's final moments. The idea is hauntingly beautiful. As a star's core vanishes behind an event horizon, the surrounding material could release one last, desperate pulse of particles and gravitational waves, a cosmic farewell before the darkness takes over. The hunt for these signals is like listening for a whisper in a hurricane. During a supernova, trillions of neutrinos flood outward, followed by the star's explosive death throes. But buried in that noise might be a second, subtler neutrino burst, a telltale spike caused by the newborn black hole's first gulp of infalling matter. In 2020, detectors near the Supernova Remnant SN 2022 JKX caught a peculiar neutrino pattern, an initial surge, then a quieter but sharper peak milliseconds later. Could that have been the moment the black hole swallowed its first meal? The data isn't conclusive, but it's the closest we've come to catching a singularity in the act of forming. Then there's the gravitational wave angle. When black holes collide, the mergers send ripples through spacetime with characteristic chirps. But a lone black hole being born might produce something different, a low frequency, ringing, as the event horizon settles into its final shape. LIGO and Virgo, the gravitational wave observatories, are tuning their instruments to listen for these faint echoes. The challenge, distinguishing them from the supernova's own gravitational shudder. It's like trying to pick out a single violin's note from a symphony orchestra's crescendo. The stakes couldn't be higher. If we can isolate these signals, we'd have direct proof of a black hole's formation, something no telescope can see. More than that, the precise timing between a supernova's light, neutrinos, and gravitational waves could reveal the black hole's birth, mass, spin, and even the conditions inside the collapsing core. Imagine rewinding the tape of stellar death and watching, millisecond by millisecond, as matter crosses the point of no return. Yet the universe loves to tease us. Some models suggest the quietest black holes might form without any cry at all, like a shadow slipping silently into a darker room. Others predict exotic intermediate states, like temporary quasi-black holes, that hover between neutron stars and singularities before fully collapsing. The only way to know, keep watching, waiting, and refining our detectors, because somewhere out there a star is about to die. And when it does, it might finally tell us how black holes are born. Now let's turn our gaze deeper into the past. Supernovae don't just shape the present universe, their light travels for millennia, carrying stories from cosmic epochs long gone. Some of these ancient explosions left behind faint, light echoes, ghostly reflections bouncing off interstellar dust that reach us centuries after the original blast. It's like hearing an echo in a canyon, but instead of sound, it's the afterglow of a star that died before humans walked the Earth. One of the most famous examples is Tycho's supernova, which lit up the sky in 1572. While the original explosion faded centuries ago, modern telescopes have caught its light still bouncing off dust clouds 400 light-years away. By analyzing these echoes, astronomers reconstructed the explosion's spectrum, proving it was a Type Ia supernova despite occurring centuries before such classifications existed. But the real jackpots are echoes from supernova lost to history. In 2008, astronomers discovered a faint ring of light near the Large Magellanic Cloud, the reflected glow of a supernova that erupted around 1600. Unseen by any human observer. Its light traveled outward, hit a dust cloud, and ricocheted toward us 400 years later like a message in a bottle. These delayed signals let us study explosions we never witnessed firsthand, turning interstellar dust into a cosmic DVR. The most mind-bending part, some echoes might still be on their way. Betelgeuse, the red supergiant in Orion's shoulder, could have already gone supernova, and its light might be racing toward us right now, with echoes set to arrive decades or even centuries after the initial flash. It's a reminder that the universe's history isn't written in stone, but in light, and we're only just learning how to read it. Light echoes are the universe's way of hitting rewind, letting us witness stellar explosions long after they've faded from the sky. Picture this, a supernova erupts in 1572, dazzling observers like Tycho Brahe, then vanishes into history. centuries later, its light, having traveled billions of miles, finally bounces off a distant dust cloud and arcs back toward Earth, offering astronomers a second chance to study the event with tools Bra couldn't have dreamed of. These ghostly reappearances aren't just cosmic nostalgia, they're time capsules preserving the fingerprints of ancient cataclysms in photons that took the scenic route to reach us. Take the case of Cassiopeia A supernova remnant from the late 17th century. No one recorded its explosion, perhaps obscured by interstellar dust, but its light echoes, discovered in 2004, revealed details no modern telescope could catch firsthand. By analyzing the reflected light spectrum, researchers determined the original star was a red supergiant that expelled massive shells of gas before detonating. It's like finding an old, faded photograph and restoring it to full color, uncovering moments lost to time. What makes these echoes so valuable isn't just their delay, it's their distortion. As light ricochets off dust at different angles, it creates a prism effect, splitting the supernova's light into wavelengths that expose elements like titanium and chromium in unprecedented detail. In 2008, echoes from a mystery explosion near the constellation Carina showed bizarrely high levels of uranium, suggesting the original star might have been part of a rare binary system where nuclear reactions ran wild. These aren't just reflections, they're cosmic autopsy reports, revealing how stars died before humanity even understood what stars were. But the real magic happens when echoes collide literally. Some supernova light bounces off multiple dust clouds, arriving at Earth years or even decades apart. By comparing these staggered signals, astronomers can reconstruct the explosion in 3D, like piecing together a shattered vase from its scattered fragments. When researchers mapped echoes from the 1572 Tycho supernova, they found the blast wave wasn't spherical but lopsided, evidence that the white dwarf detonated unevenly, a clue that could rewrite models of Type Ia explosions. Now shift gears to remnants that shouldn't exist. While most supernova debris cools and fades over millennia, a handful defy the cosmic rulebook by glowing brighter with age. Take the so-called green monster of supernova remnant W50. Discovered in radio wavelengths, this structure pulses with energy like a cosmic defibrillator, its shock waves accelerating particles to near light speed centuries after the explosion. The culprit, a hidden neutron star, beaming energy into the remnant like a ghostly lighthouse keeper tending his lamp. Then there's the case of G328.4 plus 0.4, a remnant that emits gamma rays with no visible power source. Some theorists suggest it might harbor a quark star, a hypothetical state of matter so dense protons and neutrons dissolve into free-floating quarks. If proven, it would mean supernova can leave behind more than just neutron stars and black holes. They might forge entirely new classes of celestial objects we're only beginning to imagine. These outliers aren't just scientific curiosities, they're stress-testing the laws of physics. When a remnant like KES 75 emits X-rays that fluctuate with no clear pattern, or when Puppy's A shockwaves accelerate particles faster than our best accelerators, it's a reminder that the universe still holds wild cards. Every anomaly is a crack in our understanding, waiting to be pried open. And as telescopes grow sharper, we're not just solving mysteries, we're discovering how much we still don't know. Deep in the wreckage of exploded stars, nature runs a particle accelerator that puts our most advanced machines to shame. Supernova remnants can hurl protons and atomic nuclei across the cosmos at nearly the speed of light, energy so extreme that a single subatomic particle can carry the punch of a fastball pitch. These cosmic rays constantly bombard Earth, yet for over a century their origin story has been missing key chapters. The smoking guns are finally coming into focus, and they're rewriting the rules of high-energy physics. Take the remnant RxJ171 3.7-3946. When astronomers pointed the Chandra X-ray Observatory at this twisted metal graveyard, they spotted something extraordinary: X-rays fluctuating in perfect sync with gamma rays. This wasn't random noise, it was the signature of electrons spiraling along magnetic field lines at 99.9% light speed. The kicker: the particles weren't just being swept up by shock waves, they were getting multiple boosts like a pinball ricocheting between bumpers, each collision adding more energy. Then there's the turbulence factor. In remnants like Cassiopeia A, radio telescopes have mapped chaotic whirlpools where magnetic fields twist into knots a light year across. These aren't smooth accelerators, they're cosmic mosh pits where particles get tossed between eddies, gaining speed with every violent encounter. Picture a surfer catching not one wave, but dozens in rapid succession, each one propelling them faster until they're skimming the ocean at impossible speeds. That's what happens to protons in these turbulent stellar graveyards. But the real game changer came when researchers studied the remnant W44. Its gamma-ray emissions revealed something shocking: particles were being accelerated not just at the leading shock wave, but throughout the entire structure. This suggests magnetic reconnection, a process where tangled field lines suddenly snap and reorganize, might be flinging particles sideways with unbelievable force. It's like discovering a hidden second engine in what we thought was a single propeller plane. The implications reach far beyond astronomy. If we can decode these natural accelerators, we might unlock new ways to generate particle beams here on Earth, potentially shrinking mile-long colliders into more compact designs. Already, lab experiments are mimicking remnant conditions using powerful lasers to create miniature shockwaves. The results are eerily similar to what we see in space, hinting that the universe holds blueprints for technologies we've yet to imagine. Yet mysteries remain. Some cosmic rays arrive with energies beyond what any known remnant should produce, suggesting even more powerful cosmic engines might be lurking in the dark. Others show chemical fingerprints pointing to exotic sources like pulsar wind nebulae or colliding galaxies. Every new discovery peels back another layer, revealing just how much we still have to learn about nature's ultimate particle cannons. One thing's certain: when stars die, they don't fade quietly. They go out with a bang that echoes across the universe, shaping everything from Earth's atmosphere to the future of physics itself. History hides its greatest explosions in plain sight, their remnants scattered across the sky like shrapnel from cosmic grenades. Take Kepler's supernova, the brilliant spectacle that lit up Earth's skies in 1604. For centuries, astronomers assumed it was a textbook example of a white dwarf detonation. But when modern telescopes analyzed its remnant, they found traces of silicon and iron moving at different speeds, chemical fingerprints suggesting something far more chaotic than a simple stellar explosion. The leading theory: a white dwarf might have pulled material from a companion star until it reached critical mass, but instead of a clean detonation, the interaction triggered a messy, lopsided blast that left an oddly layered debris field. Then there's SN 1006, the guest star, so bright it cast shadows on Earth for weeks. Its remnant, a sprawling web of filaments in the constellation Lupus, glows with X-rays that shouldn't be possible from a standard type Ia supernova. Spectral analysis reveals oxygen and neon racing outward at nearly 20 million miles per hour, elements typically found in core collapse explosions, not white dwarf deaths. This has led to a radical idea. What if SN 1006 was a white dwarf that somehow reignited fusion in its outer layers before exploding? Picture a dying ember suddenly bursting back into flame just as it's about to fade. But the real head-scratchers are the hybrid remnants. G130.7 plus 3.1, a faint bubble in Cassiopeia, shows chemical signatures of both a white dwarf and a massive star explosion. One wild hypothesis suggests this could be evidence of a white dwarf spiraling into a red giant's core, a stellar Russian nesting doll that detonated in stages. Others propose these anomalies might be signs of failed pair instability supernova, where stars massive enough to obliterate themselves instead left behind bizarre half-collapsed remnants. Every discrepancy in these ancient crime scenes forces us to rethink stellar life cycles. Kepler's remnant challenges our assumptions about white dwarf behavior. SN 1006 hints at exotic explosion mechanisms we haven't modeled, and the hybrids, they might represent entirely new classes of stellar deaths we've yet to classify. It's like discovering a fossil that blends features of mammals and reptiles, proof that nature's rulebook has missing chapters. Now shift focus to the remnants that defy time itself. Most supernova debris lingers for millennia, but some fade in mere centuries, vanishing before our eyes like cosmic mirages. The Crab Nebula, 960 years post-explosion, still pulses with energy from its neutron star heart. Yet remnants like G190.0 plus 0.4, just a few thousand years old, have already dissolved into near invisibility. The difference: environment. A supernova detonating in dense interstellar gas gets preserved like a fly in amber, its shock waves constantly reheating the surrounding material. But in the sparse voids between stars, remnants expand unimpeded, dissipating their energy into the void like a sigh in an empty room. Even stranger are the ghost remnant structures detected in radio waves but invisible in other wavelengths. These faded shells, like Da 530 in Cygnus, might be the last breaths of supernova that erupted tens of thousands of years ago. Their almost transparent gases bear traces of heavy elements, floating like smoke long after the fire has died. Studying these phantoms is like reconstructing a dinosaur from a single bone. We have to extrapolate an entire stellar life story from the faintest of echoes. What makes these fleeting remnants so valuable is their scarcity. For every 100 supernova, maybe one leaves behind a rapidly fading wreck. That suggests most stars die in environments we rarely consider, perhaps in galactic halos where gas is thin, or inside dense molecular clouds that absorb their energy. Each discovery peels back another layer of stellar diversity, proving that how a star dies depends as much on where it lives as on what it's made of. And as our telescopes grow sharper, we're not just solving mysteries, we're learning that the universe has been quietly showing us stellar death in all its forms. We just had to know where to look. Most supernova remnants linger for millennia, their glowing filaments etched across the cosmos like cosmic graffiti. But every now and then, astronomers catch a ghost, a stellar wreck that vanishes before our eyes. Take SN 1885A, the first supernova photographed in another galaxy. When it erupted in Andromeda, astronomers eagerly trained their telescopes, expecting decades of observation. Yet within a few years, the remnant had all but disappeared, fading like a dying ember. This wasn't a trick of the light. The debris field had genuinely dissolved, leaving behind only whispers of its existence in ultraviolet spectra. What makes these ephemeral remnants so baffling isn't just their brevity, it's the physics behind their vanishing act. Normally, supernova shocks heat surrounding gas to millions of degrees, keeping it luminous for ages. But in rare cases like SN 1885A, the explosion might occur in a near-perfect void, a cosmic clean room, with almost no material to energize. Without interstellar gas to collide with, the remnant shockwave has nothing to illuminate, like a firework detonating in an empty stadium. Alternatively, the star itself might have been unusually lean, ejecting so little mass that its debris disperses too quickly to form lasting structures. Then there's the exotic possibility. Some remnants might fade because they're powered by mechanisms we don't yet understand. Recent studies of the faint, fast-disappearing remnant G 130.7 plus 3.1 revealed odd chemical ratios, hints that radioactive decay or magnetic fields could be draining its energy abnormally fast. It's as if these remnants have a hidden off switch, collapsing inward or dissipating their heat through channels invisible to our instruments. The real value of these fleeting ghosts lies in their rarity. Like catching a glimpse of a shooting star, they offer a snapshot of a remnant's final act, a phase most supernovae take millennia to reach. By comparing short-lived remnants like SN 1885 with longer-lasting ones, astronomers can piece together how shockwaves lose energy, how debris mixes with interstellar space, and ultimately, how the universe recycles star stuff. But the plot thickens when we consider remnants that don't just fade, they never glow at all. Enter the dark supernova, explosions detected solely by their gravitational waves or neutrino emissions, with no visible light to mark their passing. These invisible cataclysms might occur in dense dust clouds, their light absorbed before it can escape, or involve stars that collapse directly into black holes without the usual fireworks. The most chilling possibility: some supernova might be dark because they're fundamentally different, perhaps powered by dark matter annihilation or other physics we've yet to imagine. Every missing remnant, every ghostly echo, is a reminder that the universe still holds its cards close. For every Crab nebula blazing defiantly across the centuries, there could be 100 shadow stellar deaths that passed unnoticed, their stories written in darkness rather than light. And as our detectors grow more sensitive, we're not just hunting for what's visible, we're learning to see the invisible, to trace the outlines of the universe's best-kept secrets. Dark remnants are the universe's best-kept secret supernova that vanish before they're even seen. While most stellar explosions paint the cosmos with brilliant nebulae, some leave behind nothing but shadows. The culprit: thick curtains of interstellar dust swallowing light whole, or black holes forming so abruptly they snuff out the explosion before it begins. Imagine a star collapsing in total silence, its death throes muffled by the very fabric of space. Until recently, these ghosts were pure speculation. But now, infrared telescopes like the James Webb Space Telescope are peeling back the dusty veil, catching whispers of heat where visible light fails. Take the case of SN 2020-JXF, a supernova detected not by its light, but by the sudden warmth radiating from a seemingly empty patch of sky. Follow-up observations revealed a dense cocoon of carbon-rich dust, a stellar funeral shroud absorbing nearly all visible radiation. Only the faintest infrared glow betrayed the cataclysm beneath. This discovery hints at an entire hidden population of dark supernova, their remnants lurking just beyond our sight. Even more intriguing are gravitational wave detectors like LIGO, which have caught ripples in space-time from mergers we never saw optically. Could some of these events be failed supernova, stars imploding into black holes without the usual fireworks? The numbers are startling. If current surveys are correct, for every supernova remnant we've catalogued, there might be 3 or 4 cloaked in darkness. That would mean our census of stellar deaths is woefully incomplete, like trying to study Earth's weather while ignoring every storm that forms over the ocean. The implications ripple across astronomy. If dark remnants are this common, they could be quietly shaping galaxies, seeding black holes, and spreading heavy elements in ways our models don't account for. Yet the darkest remnants might not be hiding at all. They could be illusions, Some missing supernova might belong to a stranger category, stars that shouldn't explode in the first place. Theoretical models have long predicted that certain massive stars, particularly those rich in oxygen and neon, would collapse directly into black holes without a visible explosion. But in 2023, the supernova 2023 IXV upended expectations. Its progenitor was precisely this type of star doomed, by all accounts, to vanish silently. Yet it detonated with surprising vigor, leaving astronomers scrambling to explain why. This contradiction exposes a crack in our understanding of stellar death. Perhaps magnetic fields or rapid rotation can force a silent collapse to fail, triggering an explosion against all odds. Or maybe these stars are more chemically complex than we thought, with layers of unstable elements that ignite like hidden fuses. Whatever the answer, one thing's clear: the universe has more than one way to silence a star, and as we probe deeper into the shadows, we're not just finding hidden remnants, we're discovering that the rules of stellar death are far more flexible than we ever imagined. Type Ia supernova have long been astronomy's gold standard, literally. These brilliant explosions of white dwarf stars shine with such predictable brightness that scientists use them as standard candles to measure cosmic distances. But peel back the curtain and the story gets messy. Some of these cosmic yardsticks flicker too bright or too dim, explode too fast or too slow, or leave behind chemical fingerprints that don't match the textbook models. Take SN 2014J, a Type Ia that erupted in nearby galaxy M82. Instead of the classic uniform brightness, it flickered unpredictably in the days before detonation, as if the star was gasping for breath before its final act. Then there's SN 2003FG, which burned twice as long as expected, its light curve stretching like taffy in the cosmic oven. So what's throwing these explosions off script? One emerging theory suggests there are multiple roads to a Type Ia supernova. The classic model involves a white dwarf siphoning material from a companion star until it hits a critical mass and detonates. But some white dwarfs might collide head-on, creating a more violent, asymmetrical explosion. Others could ignite under bizarre conditions, like merging with another white dwarf in a slow-motion death spiral. The evidence lies in the debris. Normal Type Ia remnants like Tycho's supernova show smooth layers of silicon and iron, but oddballs like SNR 0509-67.5 in the Large Magellanic Cloud sport clumps of titanium and chromium elements that only form in ultraviolet collisions. The stakes are higher than just stellar forensics. If Type Ia supernova aren't as uniform as we thought, it could send shockwaves through cosmology. These explosions are the backbone of our measurement of the universe's expansion, the very data that revealed dark energy. A slight miscalibration in their brightness could mean we've misjudged cosmic distances, skewing our understanding of everything from galaxy formation to the universe's ultimate fate. It's like realizing the ruler you've used to map the cosmos has unmarked inches. Now shift focus to where these stellar fireworks leave their scars. Supernova remnants don't always rest in peace. Some cluster in galactic graveyards, their overlapping shockwaves creating cosmic echo chambers. The Cygnus Loop, a sprawling wreckage 3 times the size of a full moon, is actually multiple remnants piled atop one another, their gases intertwining like ghostly braids. Then there's the Vela complex in the southern sky, where at least 3 supernovae detonated within a few hundred light-years of each other, their combined energy sculpting vast bubbles in the interstellar medium. These crowded necropolises are more than just celestial curiosities, they're pressure cookers for star formation. When shockwaves from multiple remnants collide, They can compress gas clouds into new stellar nurseries, proving that even in death, stars pave the way for rebirth. Yet the densest remnant clusters hide the strangest secrets. Near the galactic center, Chandra X-ray Observatory has spotted a bizarre concentration of supernova debris orbiting the Milky Way's central black hole. Some show traces of rare isotopes like aluminum-26, suggesting they formed from stars born in a radically different environment, perhaps a long-vanished dwarf galaxy swallowed by our own. Others flicker with gamma rays, hinting at hidden pulsars or even dark matter interactions. These ghostly gatherings are cosmic palimpsests, their layered histories waiting to be decoded. What's clear is that the universe refuses to be pigeonholed. Just when we think we've cracked the code on stellar deaths, anomalies emerge whispering that there's more to learn, more to question, and more wonders lurking in the darkness. And as we piece together these puzzles, we're not just mapping the stars, we're rewriting the very language of the cosmos. Galaxies have memory not in books or stone, but in the ghostly fingerprints of dead stars. Scattered across the Milky Way are eerie congregations where supernova remnants cluster like tombstones in a cosmic graveyard. The Cygnus Loop isn't just one stellar corpse, it's a layered burial ground where multiple explosions have stacked their debris over millennia. The Vela complex in the southern sky cradles at least 3 supernova remnants tangled together, their shock waves intertwining like spectral dancers. Why do these stellar ghosts gather in such strange, crowded necropolises? The answer might rewrite our understanding of galactic archaeology. One clue lies in the turbulent nurseries where stars are born. Massive stars rarely form in isolation. They emerge in dense clusters, living fast and dying young. When these stellar siblings explode in rapid succession, their remnants pile up like layers of ash from consecutive volcanic eruptions. The Carina Nebula, a cauldron of star formation, shows signs of this phenomenon. Its gas clouds bear the scars of multiple supernovae whose shockwaves collided, compressing new stars into existence even as their predecessors faded. It's a self-perpetuating cycle. Stars die violently, triggering new births which eventually die and repeat the process. But some clustered remnants tell a darker story. Near the galaxy's core, astronomers have found a bizarre concentration of supernova debris orbiting Sagittarius A, our central black hole. These remnants are oddly rich in rare isotopes like aluminum-26, a fingerprint of stars born in extreme environments. The leading theory: these might be the last survivors of a dwarf galaxy devoured by the Milky Way billions of years ago. Its stars ripped apart, their explosive deaths now marking the grave of their lost home. It's celestial paleontology, where each remnant is a fossil hinting at our galaxy's violent mergers. Then there's the dark matter wildcard. Simulations suggest invisible halos of dark matter could act as gravitational traps, funneling supernova debris into specific regions over cosmic time. In the gamma-ray glow of remnants like W44, researchers have spotted anomalies that might reveal dark matter particles annihilating at their edges. If proven, it would mean these graveyards aren't just memorials to dead stars, they're signposts to the universe's most elusive substance. The afterlife of these remnants is just as fascinating as their origins. In crowded necropolises, overlapping shockwaves create particle accelerators of unimaginable scale. When debris from one supernova slams into another's, it can generate energies that dwarf the Large Hadron Collider, natural laboratories where matter is pushed to extremes we can't replicate on Earth. The Fermi bubbles, giant structures towering above the Milky Way's core, might be the ultimate example, evidence of ancient supernova clusters whose combined energy punched holes in galactic gas, shaping the very architecture of our celestial home. Yet the most haunting question remains unanswered. If supernova cluster in patterns, could their timing follow hidden rhythms? Some researchers speculate these graveyards might encode a supernova clock, with explosions triggering chain reactions across star-forming regions. It's a cosmic domino effect where one stellar death sets the stage for the next, a reminder that in the grand tapestry of the galaxy, no star truly dies alone. And as we map these ghostly gatherings, we're not just studying stellar endings, we're reading the Milky Way's autobiography, written in the ashes of its most violent moments. Every supernova remnant has an expiration date, a moment when its glowing filaments dissolve back into the interstellar medium like sugar in hot tea. But unlike the violent spectacle of their birth, these final acts play out over hundreds of thousands of years in slow motion and half-light. Take the faint, wispy remains of supernova G 150.3 plus 4.5. Once a brilliant nebula visible to ancient astronomers, it's now barely detectable in radio wavelength, its shockwaves having traveled so far that they've essentially run out of gas. Yet even in its twilight, this remnant clings to existence through faint magnetic knots and stubborn pockets of ionized particles, like embers refusing to cool. The mechanics of this cosmic fade-out are more complex than simple dispersal. As remnants expand, their shockwaves plow through the interstellar medium, creating turbulent eddies where magnetic fields twist into intricate braids. These structures act like cosmic sponges, trapping particles and energy long after the visible glow has faded. The Veil Nebula's western filament, nicknamed the Witch's Broom, shows this process in action. Though its optical emissions are dimming, radio telescopes reveal invisible magnetic skeletons still vibrating with energy, channeling particles along unseen highways. It's proof that remnants don't just vanish, they transform, leaving behind invisible architecture that shapes future star formation. Then there's the question of chemical legacies. When a remnant finally blends into the galactic background, it doesn't disappear. It seasons the interstellar soup with heavy elements. The Orion Eridanus superbubble, a vast cavity carved by multiple supernova, demonstrates this on an epic scale. Though its individual remnants are long gone, spectroscopic analysis shows the region is laced with enhanced levels of iron, oxygen, and neon, the atomic ashes of dead stars now woven into new molecular clouds. This recycling isn't tidy. Some elements clump into dust grains that drift for eons, while others bond into complex molecules that might someday seed planetary systems. The final stages of a remnant's life could also hide surprises about galactic ecology. In 2021, astronomers studying the faint remnant HB21 discovered something unexpected: dense, cold gas clouds lingering where the shockwave had passed centuries earlier. These weren't just leftover debris, they were interstellar gas that had cooled and recondensed behind the fading shock, like dew forming after a storm. If this phenomenon is common, it would mean remnants don't just scatter material, they might also trigger localized pockets of star formation long after their visible demise, like celestial phoenixes birthing new stars from their own ashes. Yet the darkest remnants might leave no trace at all. Theoretical models suggest some supernova, particularly those in sparse galactic voids, could expand until their particles become too diffuse to detect, vanishing without even a magnetic fingerprint. Others might collide with neighboring remnants, their energies canceling out like waves meeting in opposite phases. The true end of a remnant's life might not be a moment, but a gradient, an imperceptible transition from structure to chaos, from memory to oblivion. This slow fade carries cosmic consequences. Every atom recycled from a remnant's death throes becomes part of future stars, planets, or even living organisms. The calcium in your bones, the iron in your blood, they might have once ridden the shockwaves of a dying star's final act, only to find themselves here, billions of years later, as part of you. And as we learn to read these last whispers of stellar remnants, we're not just studying endings, we're tracing the invisible threads that bind the universe's past to its future. Now shift focus from stellar ghosts to celestial threats. While most supernovae are distant spectacles, a handful have erupted close enough to Earth to leave scars in our planet's geological record. And some, lurking in our cosmic backyard, could one day deliver a blast powerful enough to rewrite history. The question isn't just about how remnants fade, but whether we're prepared for the next supernova that hasn't even exploded yet. Beneath our feet, buried in ancient rock layers, lies evidence of cosmic violence that once rained down on Earth. Across multiple continents, geologists have uncovered spikes of radioactive iron-60 isotopes, a telltale signature with no natural terrestrial source. These subatomic fingerprints point to an unsettling truth. Within the last few million years, at least 2 supernovae exploded terrifyingly close to our solar system, bathing our planet in deadly radiation. One event, dated to roughly 2.6 million years ago, coincides eerily with the Pliocene marine megafauna extinction, a time when massive sea creatures vanished abruptly from the fossil record. Could stellar explosions from light years away have triggered ecological chaos on Earth? The physics behind this interstellar assault is chilling. When a supernova detonates within 50 parsecs, about 160 light years, its gamma-ray burst and ensuing cosmic rays can strip away Earth's protective ozone layer for centuries. Without this shield, ultraviolet radiation from our own sun would pound the surface, mutating DNA and collapsing food chains, but the real threat comes from the aftermath. As the remnant shockwave plows through interstellar space, it drags a turbulent wake of high-energy particles that can bombard our planet for millennia. The young local bubble, a cavity of hot gas surrounding our solar system, might be the scar tissue from one such ancient catastrophe, a celestial wound still healing. Betelgeuse's recent dimming episodes have reignited concerns, but this red supergiant isn't our most imminent threat. At 640 light-years away, its potential supernova would likely dazzle rather than damage. Far more worrying are silent killers like Ik Pegasi b, a white dwarf just 150 light-years distant, creeping toward critical mass as it steals material from its companion star. Or the blue hypergiant Rho Cassiopeiae, whose violent eruptions hint at instability. Unlike Betelgeuse's predictable fireworks, these stars could detonate with little warning, their remnant shockwaves reaching us within a human lifetime. Decoding past supernova impacts requires forensic astronomy. By studying the distribution and motion of nearby remnants like the Gum Nebula or the Vela Junior supernova remnant, a suspected culprit in Earth's iron-60 deposits, we can reconstruct their explosive histories and trajectories. Advanced simulations now suggest our solar system may have passed through multiple remnant lobes during its galactic orbit, with some models pointing to a close encounter with the Geminga pulsar's debris field just 90,000 years ago. These celestial near misses leave no visible crater, but their isotopic signatures in deep sea crusts and lunar regolith reveal an invisible bombardment. The future of remnant research could become a matter of planetary survival. Projects like the Laser Interferometer Gravitational Wave Observatory aren't just hunting black hole collisions. They're fine-tuning their sensitivity to catch the gravitational waves of nearby core collapse supernova hours before light reaches us. Early warning might one day allow us to shield satellites, protect astronauts, or even alter atmospheric chemistry to mitigate ozone damage. Meanwhile, surveys like Gaia are mapping the positions and velocities of every known supernova progenitor within 1,000 light-years, calculating which stars will pose threats and when. Yet the greatest revelation lies in the patterns we're just beginning to discern. The Scorpius-Centaurus OB Association, a nearby stellar nursery, has birthed 20 supernovae in the last 11 million years, some potentially close enough to have brushed Earth with their remnants. This suggests we don't orbit the galaxy in peaceful isolation, but in a shooting gallery where stellar deaths come in clusters. As we peer into the future of remnant research, we're not just solving cosmic mysteries, we're learning to read the sky as our ancestors once did, not for myth or navigation, but as an early warning system for the ultimate celestial storm. The question isn't whether another near-Earth supernova will occur, but when, and whether we'll be ready to face the aftermath written in stardust and stone. The night sky has always whispered its secrets, but now, for the first time in history, we have the tools to hear them clearly. The James Webb Space Telescope, with its infrared eyes, peers through cosmic dust like never before, revealing supernova remnants hidden for centuries. In the Carina Nebula, JWST spotted the faint glow of a 1,000-year-old remnant previously invisible to optical telescopes, its delicate filaments laced with organic molecules that could seed future planets. Meanwhile, AI algorithms sift through mountains of radio data, identifying ghostly remnants like G1 5.9 plus 0.4, a structure so diffuse human eyes would have overlooked it forever. These aren't just incremental upgrades, they're revolutionizing how we see stellar death. Take the case of AI-assisted discovery in the galactic plane. Traditional surveys might spot a dozen remnants in a decade, but when researchers fed 20 years of radio observations into machine learning systems, the algorithms uncovered over 50 new candidates in months, some with bizarre, asymmetrical shapes that defy existing models. One, dubbed the cosmic jellyfish, sports tentacle-like tendrils stretching 30 light-years, suggesting its progenitor star exploded near a black hole's gravitational grip. These aren't just new objects, they're clues to environments we never thought could host supernova. And with AI now predicting remnant ages and progenitor types from spectral fingerprints alone, we're essentially teaching machines to read stellar obituaries. The real game changer lies in combining these tools. JWST infrared spectra, when paired with AI analysis, can decode remnant chemistry atom by atom. In the puppies A Remnant, this duo detected unexpected traces of buckeball soccer ball-shaped carbon molecules that could shield prebiotic compounds in space. It raises a staggering possibility. Might supernova remnants be cosmic greenhouses, forging and protecting the very ingredients life needs? Then there's dark energy. By using AI to map thousands of Type I remnants in distant galaxies, astronomers are testing whether these standard candles truly burn uniformly across cosmic time, a crucial check on whether dark energy's grip on the universe is changing. Yet the most profound revelations might come from what these technologies can't yet explain. JWST images of Cassiopeia show regions where physics seems to break down pockets of extreme turbulence that even supercomputers struggle to simulate. And in the remnant G327.1-1.1, AI flagged an eerie radio oscillation matching no known pulsar or black hole signal. Could it be something entirely new, a quark star, or a defect in spacetime itself? Every unanswered question is a doorway. As we stand at this crossroads of silicon and starlight, the line between discovery and philosophy blurs. These tools don't just show us how stars die, they force us to confront how much we've underestimated the universe's creativity. From the possibility of life's building blocks forged in chaos to the chance that remnants encode secrets of dark energy, we're no longer just observers of cosmic history, we're active participants in its decoding. And with each technological leap, we're reminded the universe's greatest mysteries aren't hiding in darkness. They're waiting for us to look in the right way. Every atom in your body, every breath you take, every mountain and ocean on Earth, all of it was forged in the heart of dying stars. Supernova aren't just endings, they're the universe's greatest alchemists, transforming simple elements into the building blocks of planets, oceans, and life itself. Picture a star exploding with such force that it flings its innermost elements, carbon, oxygen, iron, even gold, across light years of space. Over eons, these atoms drift through cosmic clouds until gravity pulls them together into new stars, new worlds, and perhaps new life. This isn't poetic speculation, it's scientific fact. The calcium in your bones once floated in the debris field of a stellar explosion billions of years ago. The iron in your blood was likely part of a supernova remnant before it found its way into Earth's crust. But the story gets even more astonishing. Recent studies of meteorites, the oldest rocks in our solar system, reveal microscopic crystals rich in radioactive isotopes like aluminum-26. These crystals couldn't have formed in the quiet cradle of our young sun. Instead, they carry the unmistakable signature of a nearby supernova's shockwave, which may have triggered the collapse of the solar nebula that birthed our planetary system. In other words, without a star's violent death, Earth and you might never have existed. It's a humbling thought. The same cataclysm that obliterates stars also sets the stage for life's emergence. Now zoom out to the grandest scale. Across the Milky Way, supernova remnants act like cosmic compost heaps, enriching star-forming regions with heavy elements. The Orion Nebula, a stellar nursery visible to the naked eye, is laced with sulfur and silicon from ancient explosions. The pillars of creation, those iconic towers of gas and dust, are being sculpted by shockwaves from long-dead stars. Even more mind-bending, the elements essential for life, carbon, nitrogen, phosphorus, are disproportionately abundant in regions where supernovae have erupted. It's as if the universe has a recipe and stellar explosions are the key ingredient. This raises a profound question. If supernovae are universal gardeners, sowing the seeds of life throughout the cosmos, could other worlds have reaped the same harvest? On Enceladus, Saturn's icy moon, plumes of water vapor contain organic molecules that might trace their lineage to stellar explosions. In the atmosphere of K2-18b, a distant exoplanet, telescopes have detected hints of water vapor alongside potential biosignatures, all elements delivered, at least in part, by supernova debris. The implications are staggering. Life elsewhere, if it exists, might share the same stellar ancestry as life on Earth, a family tree rooted in the ashes of dead stars. Yet the cosmic cycle doesn't end there. Some scientists speculate that supernova might not just provide life's ingredients, they could also influence its evolution. When remnants like Vela or Geminga erupted near Earth in the distant past, their radiation may have triggered mutations in early organisms, accelerating evolutionary change. It's a controversial idea, but fossil records show spikes in biodiversity coinciding with periods of heightened cosmic ray exposure. Could stellar deaths have nudged life toward complexity? As we stand beneath the stars, we're not just observers of this grand cycle, we're participants. Our bodies, our world, and every living thing are threads in a tapestry woven by stellar explosions. The oxygen you breathe, the metals in your phone, the DNA in your cells, all of it carries the echo of a star's final moments. And when our sun eventually dies, its remnants will join the cosmic dance, scattering elements that might one day seed life around another star. The universe doesn't just create and destroy, it recycles, rebuilds, and remembers. We are stardust given consciousness, the universe's way of knowing itself. And that connection between the cataclysmic and the cosmic, the ancient and the alive, might be the greatest mystery of all. From the eerie silence of vanishing stars to the brilliant chaos of supernova, every mystery we've explored peels back another layer of the universe's grand design. These aren't just cosmic curiosities, they're the threads weaving together the story of everything. Take the case of phantom supernova, stars that disappear without a trace, or the zombie stars that cheat death against all odds. Each discovery forces us to rewrite the rules, proving that stellar deaths are as unpredictable as they are awe-inspiring. And then there's the alchemy, the way these explosions forge the very elements that make up our world, from the iron in our blood to the silicon in our smartphones. It's a reminder that we're not just observers of the cosmos, we're products of its most violent moments, but the real magic lies in what we haven't figured out yet. Why do some remnants glow brighter than they should, defying the laws of physics? How do stars like Betelgeuse toy with us, flickering ominously before settling back into quiet? And what about the dark remnants, the ones that vanish without a trace, leaving only gravitational ripples as their farewell? These gaps in our knowledge aren't failures, they're invitations. Every unanswered question is a door waiting to be kicked open by the next generation of telescopes, algorithms, or even amateur astronomers staring up at the night sky. The beauty of this journey isn't just in the answers, it's in the collaboration. From AI sifting through radio static to space telescopes capturing infrared whispers, humanity is piecing together this puzzle as a team. And you're part of that, whether you're a seasoned stargazer or someone who just paused to wonder about the stars, you're now part of the conversation. So keep looking up, share what fascinates you, debate the mysteries in the comments, because the next big discovery might not come from a lab or a satellite. It could start with a spark of curiosity, just like yours. The universe isn't done surprising us, and with every mystery solved, a dozen more take its place, waiting for the next curious mind to step forward and say, "What if?" If this journey through the cosmos left you as awestruck as it did us, don't forget to hit like, subscribe, and join the discussion below. The stars have been writing their stories for billions of years. Now it's our turn to listen and maybe, just maybe, add a line or two of our own. End of video. Ever wanted to be part of a cosmic detective story? You don't need a PhD or $1 million telescope, just a computer and curiosity. Across the globe, astronomers are drowning in data, with telescopes capturing more supernova candidates in a single night than traditional teams could analyze in months. That's where you come in. Projects like Zooniverse's Supernova Hunters put real telescope images in front of everyday people, training them to spot the telltale signs of stellar explosions. One volunteer, a retired teacher in Minnesota, famously flagged a flickering dot in galaxy NGC 613 that turned out to be a rare type IAX supernova, a discovery that made headlines and reshaped theories about white dwarf explosions. The process is simpler than you might think. After a quick tutorial, you're shown side-by-side images of the same patch of sky taken days or weeks apart. Your job: look for the tiny speck that wasn't there before. It's like playing Cosmic Spot the Difference, except your clicks could lead to professional astronomers training their scopes on a newfound stellar catastrophe. What makes this so powerful is the human eye's knack for pattern recognition. Software might miss a faint smudge near a bright galaxy, but our brains excel at picking out anomalies. In 2022, citizen scientists scanning data from the Pan-STARRS telescope in Hawaii identified 3 supernovae that algorithms had overlooked, proving there's no substitute for human intuition. Beyond supernova, platforms like Radio Galaxy Zoo let you trace the ghostly filaments of ancient remnants in radio telescope data, while SETI Live enlists help decoding strange signals that might, just might, be linked to dying stars. The most thrilling part, some projects stream live feeds from professional observatories, meaning you could be the first person to witness a star's death throes in real time. Imagine sipping coffee at your kitchen table as you flag a supernova still brightening toward its peak, a celestial event unfolding across millions of light years, captured because you happened to be online at the right moment. This isn't just busy work. Your contributions get folded into published research, with volunteers regularly credited in scientific papers. The Galaxy Cruise project, where users classify galaxies hosting supernova, has already contributed to studies on how stellar explosions affect their galactic neighborhoods. Even failed candidates matter when thousands of users agree a potential supernova is just a camera artifact. It helps refine machine learning algorithms to reduce false positives. You're not just hunting explosions, you're training the next generation of discovery tools. The tools keep evolving. New apps like Backyard Worlds Planet 9 incorporate augmented reality, letting you swipe through telescope data like cosmic Tinder, while AI-assisted platforms highlight suspicious regions for human verification. Some projects even pair volunteers with mentors, professional astronomers who explain the science behind your discoveries. It's a far cry from old-school astronomy, where amateurs scanned the skies with backyard telescopes. Now you can comb through data from Chile's ALMA array or NASA Kepler mission, all while wearing pajamas. What's most inspiring is how these projects democratize discovery. When a 10-year-old in Tokyo helped identify a supernova remnant in 2021, it proved that passion, not credentials, drives progress. Every time you log in, you're joining a global team. Teachers, artists, nurses, and kids, all united by wonder. The next stellar breakthrough might not come from a lab, but from your living room. And who knows, the dot you click today could unravel a mystery that's puzzled scientists for decades. The universe is speaking. All you have to do is listen.